Hello everyone, I'm going to make a few different video tutorials. In this one I want to go through OLS regression. I'm starting here with that table that I had sent around, and I will send around an updated version of this, but when we get to multiple regression, the key distinction, how you know how to navigate to one forest or another, i.e. OLS or logistic, really fundamentally depends on the dependent variable. And so if you have an interval dependent variable, interval outcome, that's when you would do OLS regression. Okay? You'd only go into logistic if you were doing dichotomous. Just a few key things. I'm not going to fully review the table. Independent variables need to be interval or dichotomous. If you have a multi-categorical variable, whether it's ordinal or nominal, you should put a I dot prefix in front of it. And what that does is sort of what we call dummy it out. Essentially creates a bunch of little dichotomous comparisons between each of the categories and the first category, which will serve as a reference group. It's essentially a little bit similar like the Bonferroni option when you're doing ANOVA. The key thing with OLS, remembering that your dependent variable is interval, can take on any number of values in a particular range. And what we're trying to do is see how each of our independent variables contributes to an estimated value in that outcome. Okay? So when you're interpreting, it's important to remember that we're looking at the estimated effect of x or x1 or x2 on the value of y for every 1 unit change in x, controlling for the other factors. Okay? Key thing when you're doing OLS, never use words like likelihood or probability or odds. Okay? Those don't apply in OLS, so make sure you scratch those out of your vocabulary when you're doing OLS regression. And then when we get into the graphing, I want to make the distinction here, but I'll make it again when I go through the example using the generic do file. We can, on the one hand, just graph the coefficients and their confidence intervals, and that's just really a graphical correlate of what you get in the table. Or we can go and use the regression output, the equation, to then calculate what are known as margins, or predicted values of y at varying levels of a specified x, holding other factors constant. And that's really, as I've said before, is where the true value of this, of Stata and other programs like this come into play, because you can really showcase for everybody, expert or layperson, what these effects look like, and translating into predicted values of y is really quite accessible for you, for me, and for everybody else. So we're going to showcase all of those things. But what I'm going to do, I'm just going to do the example that I sent around, focusing on the mining data, and I have the write-up. So I'm going to do something similar to what you see in this write-up, but I'm going to go through using the generic do file. Okay, so I'm going to pull up the data set, the mining prep data set, which I already have up, and then I'm just going to go through. And in terms of codebook, this is part of the first step in OLS, is to get to know your data. So I'm going to codebook the variables. P-fair-poor is going to be my outcome. I'm going to look at P-pov as a independent variable along with mine stat. Okay, we're going to keep it simple. It's multiple regression because I've got 2 independent variables. So we're going to run that code. And what we see, P-fair-poor ranges from 6 to 44, 37 unique values across roughly 351 cases, mean standard. So clearly an interval outcome, right? It varies across these 350 cases or counties, and so that's why we're going to use OLS regression. The P-pov variable ranges from 2.7 to 38, 371 unique values, clearly interval, right? And then we get down to the mine stat variable, range 0 to 2, 3 unique values, and we can actually see the value labels. Okay. Again, if you, whether in the code book or in the data set itself, if it's already prepped, if you can imagine or you see value labels attached to your numbers, you're dealing with categorical. There's no question about it. Okay. And this just happens to be nominal, right? But whether it's ordinal or nominal, really often doesn't matter. We're just going to need to know that it's categorical. Okay, so we're going to move on in our do file. I can look more at, use the free command, the frequency command for the categorical one, same thing for tab. And then if I want to look at the summary statistics for p-fair, poor, and p-pov. So we'll just do those one at a time. The free one just gives me, sort of the frequency distributions, and then the tab does something similar. And then the summary statistics, for the interval, we get the mean, standard deviation, min, and max. Okay, and of course you'll notice we're missing about 51 counties for p-fair, poor, so those are going to drop out as we move along. Okay. Now, if I were harvesting summary statistics to put in a descriptive statistics table, I would probably want to make sure that, since in the end I'm only going to be using 351 cases that have full data, I want to make sure that my summary statistics represented those things. So one of the things is you can use that if not missing one. So if I go back and put that in, and I can just include all the variables that will eventually find their way into my model. Start with the dependent variable, comma, p-pov, and then min stat. And I would just copy that if not missing statement, and I can just place it on all of these. Okay. You always want to put it before a comma. So if you do the summary ones like that, and then I would switch these out. So dependent variables, p-fair, poor, and the histogram. Okay. So again, if I rerun these now with that restriction, I've only got 351. I'm going to get slightly different frequencies because, again, now the counties with no p-fair, poor value are dropping out. So if I was harvesting these for a descriptive statistics table, that's how I would standardize the sample that ultimately is going to be used in my multiple regression. Okay. Same thing on here. Now they're only showing the 351 cases with full data. So then I can go down and as I say in the annotation here, it's particularly important to kind of examine your dependent variable. Sometimes you'll find that on an interval variable, it's not normally distributed at all. Sometimes the cases are really sandwiched at one end or the other. And that's just something to be aware of. We can do some adjustments, but you want to see if you're dealing with skewness or kurtosis. You could run an SK test on it, things like that, but it's more about just kind of getting a sense of your data at this point. So I'm running a histogram here. It's largely conforming to normal distribution, so I'm not too concerned. And even if it does look quite skewed, usually this method is still powerful enough to move forward with. But again, it's all about getting to know your data, and if you know the variables that are going in your model, use that if not missing and just attach it to every of your summary commands. Again, if you have comma detail, make sure it goes before the comma detail. And then you can get those sort of standardized summary statistics. Okay? So let's move on to the regression. If you have to do any prep, you would do that at that point and then rerun all of your summary data, descriptive statistics. Step one, run the regression, the full model. Now when I say the full model, it means all the variables that you plan on bringing into your regression at any point. Right? So sort of all your independent variables at once. So in this case, I can get rid of one of these. I was just showcasing how you would do the I dot prefix, but we're going to do p-fair, poor, p-pov, and I dot line stat. Okay. And let's go ahead and execute that. And I didn't have to do the if not missing because notice because they're all in the model, only cases that have data on all three are going to be included. But if you want to be super thorough, go ahead and just attach that if not missing. Right? It's not going to change anything. Okay. So I do that. So I run the full model. You run, and once you're done with the full model, you can run diagnostics on this model and make any changes. Now keep in mind that you never throw a multi-categorical variable into the model as is, right? Unless it's ordinal and you're treating it as interval. I rarely do that, right? it's always safe to I-dot them, ordinal. But if you have a rather nuanced categorical ordinal variable with 10 different categories, and it's just a control variable, yeah, you could probably get away with just throwing it in as is with no I-dot and treating it as interval. But you might consider instead collapsing some of those categories and still I-dotting it in order to keep it as a categorical. Now note, imagine the following contains all the variables, so there's the full model. Now note, if you have a categorical variable you I-dot, you'll see how each group compares to the reference group. If you want to know if non-reference groups are significantly different from one another, you can use the following test command. You'll need to know the number assigned each category. Ultimately, though, you'll plan to graph the results through coefplot and so on. So here's the thing. I'm going to just kind of briefly go through the results here. When I get a regression result like this, I notice the n. I look at the r squared, which tells me this model, in this case it's MindStat and PPOV, that model accounts for 59% of the variance across counties in p-fair poor. Okay, so that's what the r squared stands for. I largely ignore everything else here. Okay. Then I get down to my results here, and this is the effect of percent impoverished on p-fair poor controlling for mine status, just as these are the effect of mining status controlling for PPOV. Okay. Another way in which that's phrased, adjusting for or holding constant, the other variables. Okay, so it's the effect of one holding the others constant or having adjusted for them, and vice versa. Okay, so I notice this effect. This is the regression coefficient. We call this the unstandardized regression coefficient. Notice that there's a standard error associated. So this is our estimate of the effect. What Stata is doing is getting the standard error as well, which is a measure of the likelihood of sampling error. It divides your coefficient divided by the standard error to get a t-statistic. It then goes and assesses that t-statistic. What's the probability of getting that by chance, even in a world where there really is no relationship? If the p is less than 0.05, probability of that happening is less than 0.05, we can reject that premise, reject the null hypothesis, which is this p-value. And then again, we also get a 95% confidence interval. And if this p-value is less than 0.05, which you will notice in OLS regression, the confidence interval will never include 0, because 0 is not a reasonable option. Okay, so the confidence interval says, yes, here's your best estimate based on this data, but values within this range are also compatible with our data. Now they just get less compatible as they get further away from your estimate. Okay, but if 0 was included in that interval, then 0 would still be compatible and we wouldn't be able to reject the null. Okay, but our p-value is less than 0.05. We don't see obviously 0 within that interval range. Okay, and so on. So if I were to look at this, here's an interval variable, and the way this translates is for every 1 unit increase in percent impoverished, which translates to a 1 percentage point, there is a 0.65 percentage point increase in the percentage of people reporting diminished health. Okay, and it's a statistically significant effect. I just mean we have confidence that it's very likely reflecting something out there in that population of counties. Okay, and again, that's the effect of poverty rate having controlled for MindStat. Now when you get to interpreting a categorical variable like this, remember I used I dot. It left off the first category, which is non-mining status. So then essentially what it does is it dummies everything out, creates dichotomous comparisons. So this is the effect of traditional mining status on p-fair poor relative to non-mining status. So traditional counties, and this is significant, so we would report on it, traditional mining counties have an estimated p-fair poor that is 2.1 percentage points higher on average than non-mining counties. Okay, let me say that again. Traditional mining counties have a percentage of people reporting diminished health that is 2.1 percentage points higher on average than counties that don't have no mining. Okay. Again, that's just the estimate. The range that we're confident that the true parameter is in is somewhere in this range. Obviously, it doesn't include 0 because d is less than 0.05. And then for removal, same thing. It's the effect of removal relative to non-mining. In this case, removal counties have a percentage reporting diminished health that is 6.3 percentage points higher on average than non-mining. Okay. Now again, these are just always in reference to the reference group. Now, what if we want to know if the difference between traditional and removal, I see a difference, but can we be confident that there really is a difference between those two? Right? Because those are just estimates, and there's a couple of ways you can determine that. One is eyeball their confidence intervals. If those intervals don't overlap, then there is a statistically significant difference between those. It's a little more complicated than that, but that's a pretty safe rule to just go by. If their intervals don't overlap, then they're going to be significantly different from one another. But if we go back to the do file, we can actually use this test command. Now the trick here is you have to know the coding of MindStat. So if you go back up, you can see it's 0, 1, 2, so we would use 1 and 2. And we would just replace test1 MindStat against 2.MindStat. So it's basically asking, and this is what we call a post-estimation command. So it has to follow immediately the regression that you want to reference. So after you've run that regression, if you run this immediately after, it's going to basically test, are the differences or the effects on p-fair poor equal? Is traditional equal to removal? And that's going to be the null hypothesis. And can we reject that? So you can see this. Basically, if they are equal, then the effect of MindStat is minus traditional minus removal should be 0. That's the null. Can we reject it? Well, if your f value here is less than 0.05, we can reject that assumption that they're equal. Okay, so we have two different ways to determine whether categories within our categorical variable are different. Eyeball the intervals or do this test command right after your regression. Okay. So now we can move on to our running diagnostics. So we just kind of, this initial full run is more about kind of getting a lay of the land, including all of your variables, because it's really on the full model that you want to run your diagnostics. And as with ANOVA and t-test, where there were assumptions about the nature of your data, OLS, there are a number of different assumptions and issues that we want to make sure that we're not suffering from. Okay, I'm going to highlight just a few. In this do file, I skip over, I think I deleted a few of these. I focus on multicollinearity, outliers, and heteroskedasticity. There are some other issues, but they're not quite as pressing. The first one is multicollinearity. Okay? And as you read, multicollinearity is when you have a high degree of correlation among your independent variables, such that Stata or whatever program you're using has a hard time parsing out any sort of unique effects. Okay? Essentially, if you have a really high degree of correlation, you know, the two variables that are highly correlated are essentially reflecting one another. And so putting them both in, it complicates Stata's calculations. Now, technically what happens is it's causing the standard errors to inflate. And when you inflate standard errors artificially, the coefficients don't change. The coefficients are fine when you have multicollinearity. Your estimates are fine. But if your standard errors get inflated, think about your t-statistic. Your standard errors, which are your denominator, as they get inflated and grow, your t-statistic is going to shrink, right? Because it's your coefficient divided by standard error gets your test statistic. So if multicollinearity is causing an inflation in your standard errors, you want to know about it, because it might lead to you to saying that a variable has no effect or no statistically significant effect, when maybe it does. It's just suffering from this inflationary effect of multicollinearity. Okay? So it's a really simple command. It's just VIF. It follows, again, your regression, or whatever your last regression is. And again, I say there is no cut and dry, dry rules about what's a high VIF, variance inflation factor. But generally, a VIF near or above 5 is a potential concern. Now that said, if I have a small n, a small sample size, I even get a little more concerned if I'm even seeing a VIF of 3. Okay. Others will say 10. So it really differs. You know, if you have a large N, then yeah, maybe you would go with 5 to 10 or something like that. If you have a small N, you might want to investigate. Okay. Now, if multicollinearity is an issue, 2 or more variables have high VIFs, and I'm looking here, you have a number of options. Drop one or the other, run the model with one of them in, take it out, run it with the other. Kind of gives you a sense of what's going on. They're probably both going to be show an effect. Consider a composite. Are both of them sort of tapping into or relating to a common latent variable? Now again, you have to pass the conceptual test and you want to check alpha and so on, but composite is a possibility where you can get from multiple independent variables to just a single one. Or you can just leave them in and note the issue. Again, multicollinearity does not bias the estimates. The estimates are still good. It just inflates your standard errors and may inadvertently cause you to suggest that something doesn't have a statistically significant effect when it does. And so you just kind of want to play around to see if that's an issue. Okay. Now, again, if you have a categorical variable, you may see high VIFs within the categories, right? So don't let that freak you out, right? You don't see it so much here in MindStat, but sometimes within a single categorical variable, you'll see high VIFs, and they all seem to be, and none outside of that single categorical variable. Don't worry about it within categorical variables. Worry about it across different variables. Okay. So we don't have an issue here. We also want to identify influential cases or outliers. Now there are 3 different ways in which we can do this. Cook's D is a good way. I put up here that it's good to kind of go through and see if you can get all 3 to work, but ultimately you can even just use the third option as a quick go-to option. But I want to go through each of these. Cook's D. D stands for distance. It's basically, it calculates how much is any one particular case, in this case it would be a county, how much is any one case causing the estimates to move from where they otherwise would be if that case wasn't there, right? And that distance is what it's calculating. Okay? And the way we do this, you'd run your regression, and then, based on the last regression, you would calculate or predict, that's the command, and D1 is just a variable name. You could call it whatever. I'm just going to call it D1. And then comma, and you have to give it the mathematical equation. Okay, so Cook's D is telling it to calculate a Cook's D value for every county in my sample. Okay. Then I want to know what's the benchmark. And now normally the benchmark for thinking about a Cook's D, the larger the Cook's D, the more that case is causing the estimates to sway in that case's direction. Right? Usually the benchmark is 4 divided by the sample size. So I'm going to put 351 in here, and I just want to use the display as a calculator here. So I can see the benchmark is roughly a Cook's D greater than 0.0114. Okay, is going to catch my eye. One other thing I can do is sort all of my cases by their Cook's D value. And then I can list cases, and you want the case ID, that is whatever the name of your county is. So maybe I'll call it, I think it's name. And we can even do state name. And then the D1 value. And I want to make sure that I'm only listing ones where the Cook's D value is greater than whatever the value, the 0.0113. I also include if, it's less than missing, because otherwise it'll give me all the missing cases as well. So I'm going to list all those. So these are, out of the 351, these are the ones with the highest Cook's D. And remember the critical benchmark is roughly 0.011. And I'm really looking for ones that are dramatically over that. So in these first ones, Adair, Petersburg, that's not really catching my eye. Where I really start to get concerned maybe is in these last ones, where you're away from the 01s and even the 02s, and then you make a jump to 04s and 5s and 7s and so on. So I'm kind of concerned maybe about these, but even these are not all that large, right? We're not looking at 0.8s or anything like that. Most concerning is maybe Radford, Virginia, and Harrisonburg, Virginia, things like that. Okay, so I would just maybe make a note of those, write them down, write out their Cook's D values, and just kind of keep them in mind as I move along. So those are potentially outlier cases that are causing my regression coefficients to be swayed disproportionate to their number, right, obviously. So let's go to the next one. Another way to kind of identify standardized residuals is to calculate, or outliers, is to calculate what we call standardized residuals. How far off is each case from what the regression equation is predicting for their p-fair poor value? Okay. And we want to see how much error is left. And the more error that's left, the more that our regression equation, y equals constant plus coefficient times poverty rate plus, and then the mining status effects. The more that we're off, the more that those cases might be pulling on our estimates. Okay. So if you plan on predicting multiple y-hats shorthand for predicted values of y via the predict command, you may want to number them. You may want to opt to skip this step and go straight to LVR2 plot described below. But let's do this. So we're going to calculate predicted values. So these are predicted values for p-fair poor. I call it y-hat just because it's kind of the generic nomenclature. And then I'm going to, and you'll see in the data here, scroll across, based on that regression equation, for each case it predicted the percent of people reporting diminished health. Okay. And obviously we know the percentage of people reporting diminished health right over here. So 14 is what we observe. The estimated is 14.005. 17, right, we're pretty close. 20, now here's one. 22 is close to 21.98. I'm looking for ones that are departing from each other. They're all pretty good. Oh, here's one that's 21 and not 21. I'm trying to find some big ones, just eyeballing it here. They're all pretty good. But again, it shows the power of our model to offer up a predicted value that's not far off from what the observed value is. But anyway, going back to our do file, we predicted the value based on the regression output. And now we're going to predict or calculate the residual. What's the difference between what we see and what we predicted? And I'm just calling that the residual, and then the comma resid is telling it how to predict it. So run that. And then we're going to standardize those residuals, which means just turning them into z-scores. Okay. And then I'm going to sort my cases on that standardized residual. And then I'm going to list my cases, and we can go back to name and state name, right, the y-hat, the residual, the r standard, and then I'm going to leave everything else as is. Okay. Return. And I'm looking for, because we took the z-scores, that's what the r standard is, there's going to be some that are negative and some that are positive, right? Because they're all in relation to the mean. So you're looking at the extremes. And I only listed the ones that are above a particular benchmark, and the benchmark is the absolute value of 1.96. So again, we're looking at the extremes here. Harrisonburg, Radford, Charlottesville, Montgomery, or on the other end, Overton, Crittenden. And I want to, again, what are we seeing here? Harrisonburg, Radford, Campbell. There's Harrisonburg, Radford. Campbell's right there. So there's a little bit of, again, these are not tapping into the same thing. Just they're giving us clues as to which counties are either exerting the most influence on our estimates, the Cook's D, or it's the ones that we're doing the worst job at predicting their percent fair poor. So, looking at this, I'm most now concerned where there's a little bit of overlap. Harrisonburg and Radford, and Harrisonburg and Radford. So those are the two now that are starting to narrow in on as potential outliers. Okay. And then we can move on to the LVR2 plot. Now, the above two different methods of detecting outliers may or may not agree on which cases are an issue. They're just kind of clues as to potential issues. typo. A case with a large residual may not have a lot of leverage. It just depends on the presence and fit of other cases. For that reason, I like to look at the leverage residual squared plot. How much leverage, how much pull on the estimates does it have, but also how far off are we in the prediction. Cases that are high in leverage and high in their squared residual are the most curious outliers. Indeed, Cook's D is a measure that takes into account a case's leverage and residual. In the command below, case ID is whatever the variable helps you identify the case. So I'm going to use the name. Let's do this. And what you're looking for here is, again, if you anything below the red lines, either to the left or below, are usually considered sort of well within sort of the fold. Okay. Now that said, the further up they go on the y-axis, that shows they have more leverage. So Clay County has more leverage, Knox has more leverage, and so on. But at the same time, none of those counties, we're still pretty on target, or we're not missing out. Our prediction is not off. It's just that those counties have a lot of leverage. But we're not off. On the other hand, here we have, as you get further out on the right here on the x-axis, you have counties where we're missing our prediction pretty substantially. And so you sort of see anything McCreary, Campbell, Wyoming, Radford, Harrisonburg. Now those are all where we're off the mark with our prediction, most egregiously with Radford and Harrisonburg. And when I look at a LVR2 plot like this, I'm really kind of looking at the most extremes. And I might be most concerned about the McCreary, Radford, and Harrisonburg. Maybe some of these others, but they're a little less concerning. It's really about the sort of upper quadrant that you're going to be looking for cases. Okay, so just for fun, I'm going to use Radford and Harrisonburg and McCreary. I'm writing those down. So those are going to be my identified outliers. Okay? I'm going to generate a new variable called outliers. I'm going to just give all my cases a 0. Okay, so I can run that command. And then I'm going to replace outliers with a 1, but on the condition that, and you have to put the condition in here, and I'm going to do if name equals Radford, or name equals Harrisonburg. Make sure I get that spelled right. Or name equals McCreary. Now again, I might want to make sure that there aren't multiple Harrisonburgs. I don't think that's the case, things like that. But if I feel pretty confident, and in the end I should only see 3 changes in my data. So if I run that, I got 2 changes. Let me see here. So in that case, just double check Radford, Harrisonburg, and McCreary. I may have spelled McCreary wrong. So I'm going to go back and fix it. There should be a large C. Let me rerun that. It's just going to change the 1. So now I have 3 outliers. If I tab outliers, there's the 3. Okay. And again, what all that did was created a new variable, gave every county a 0, and then I replaced it with a 1 if they met those conditions. Okay. So now I've got a dummy variable or a dichotomous variable that represents outlier status. So then I can go and rerun my regression. Now often what I want to do is I want to look at the regression as it was with them in. So I'm going to copy that original command and go down to here. I'm going to rerun that. So I have that fresh in my memory. And then underneath, I'm going to rerun it again. And outliers equals 0. Okay, so I want to only include if they're a non-outlier status. So I'm going to rerun it, basically excluding the ones where outliers is 1. And you'll see that in the end. So there, in the original it's 351, now I'm down to 348 because I'm excluding those outliers. And I wanted to do that to see if excluding them, what happens with my model. Okay, and there's a few things that you do then. You check to see, by excluding your outliers, does your R-squared get better? Does the model get better at accounting for variation in Y? So mine went from 0.59 to 0.62. So there's a modest, slight improvement. Not enough that I would exclude cases on that basis, but it's something to look at. And then I look at my coefficients, and I look at the p-values and so on. And I'm looking for dramatic change. So it goes from, for percent and power, 0.65 to 0.68. Not a huge change. P-values are the same. Then I'm looking at traditional removal, 2 and 6. Some modest changes. But for me, the question is, does the story change? Right? Does the overall story change dramatically? Do the effect sizes change dramatically? And this is sort of more common sense than anything. And the answer is no. I got modest improvements in R-squared and ever so slight changes in the regression coefficients by excluding those outliers. But there's still cases. And if you leave them out, they're not in the data set. And you have to have a lot of justification for doing that. So I'm actually going to put them back in. And I'm going to note that there were some cases that sort of had high residual, standardized residuals and higher values of Cook's D, and I might report on those, but say in the end that by excluding them, the results really didn't change all that much. So I decided to leave the sample whole. Now, if you see a dramatic change in R-squared, then yeah, maybe you should consider going back and dropping those outliers out, or you see a dramatic change in the coefficients. You think that as a result that you've got a better model after that. Then talk your way through that. Okay. Now, I don't have it in the do file here, but I mentioned it in pages and elsewhere. Outliers are fascinating. If they're an outlier, there's some other factor that you aren't accounting for. You may not have data in your data set to try to figure out what that is, but outliers are often a source of our additional questions. What is it about these cases that make them so exceptional, that make our otherwise model that allows us to predict other cases pretty well, or account for other cases pretty well? What is it about these cases that might be going on that might explain it? So outliers are kind of fascinating to look at in and of themselves. Okay. But in this case, I don't really see much change, so I'm actually going to go back to the full model, the full sample, as I move along. So I'm going to rerun my full model, and then I'm going to get down to the heteroskedasticity. Heteroskedasticity is when you essentially, let me show you what that looks like. When you're better at predicting values at one versus another. So the easiest thing is imagine, sort of some X, some Y, and knowing the value of X gives you a pretty good bead on the value of Y at one end, but then as you get further up, your explanatory variable gets worse at predicting Y, right? Even if that's the line, notice how much more precise we are at one end of X. So a good example is education. Low, high. And then this could be income. We often see this in this kind of relationship, where low levels of education, you're almost always going to be pretty certain about people's levels of income. But as you get into high levels of education, you get a mixture of people with MDs and PhDs and things like that, and MBAs, and incomes can vary dramatically. Okay, that's what we call heteroskedasticity. When the error terms, right, our ability to predict and how far we are off, when our error terms are not consistent, right, across values of Y. And so you can sort of see that they are not consistent. They're not homogeneous across, in this case, our model is just X. So your assumption is that they're homoskedastic, that they're the same, it's kind of the same pattern of errors across the model. Here we have heteroskedasticity. There's variation in sort of the distribution of errors. Okay, so that's what we're trying to detect. The assumption is that you don't have that problem. The assumption is you have homoskedasticity, that you're as good at predicting low levels as high levels. Okay, so how do we check for that? We do this RVF plot line, and you're kind of looking for, this is the fitted values and this is the residuals, and you're kind of looking for an even distribution, no single pattern, and we kind of see that they vary a little bit, maybe get a little better toward the high end here. So you can kind of look for that kind of even distribution. The other thing is to do a post-estimation command, het test. And again, if we read the description here, one can begin by looking at the residual versus fitted plot. You're looking for an even distribution, kind of left to right. If the distribution looks skewed in some way, then heteroskedasticity is present. Next, you can conduct a Bruch-Pagan-Cook-Weisberg test of heteroskedasticity. The null hypothesis is the variance of the residuals is homogeneous, which is what you want. A large chi-square statistic, p less than 0.05, asks us to reject that hypothesis and thus is indicative of heteroskedasticity. So we actually have a p less than 0.05. So we actually have some degree of heteroskedasticity here. Okay, so that's an issue. Paul Allison basically says don't worry about it. But if you're doing OLS, you can make some modest corrections. So what to do about it? What if you have heteroskedasticity? It may be due to model misspecification. So maybe if we think about our predictor set, our model, and think of other possible predictors that we're leaving out, perhaps bringing those in will bring things back into focus. That's often not an option. Two, because heteroskedasticity causes standard errors to be biased, one can make use of Stata's robust option, which has Stata relax the assumption that errors are both independent and identically distributed. Complicated sentence there, but basically we can add this comma robust option, and what it will do is do some adjustments with the standard errors to kind of account for heteroskedasticity. So if we wanted to do that, we could rerun our regression. We go and pull that one up. And then add robust. And we would say that we ran the regressions with robust standard errors. Okay. And notice, nothing really changes too much. It looks actually pretty almost identical. Okay. The standard errors are a little different, right? The coefficients are the same, but the standard errors changed a little bit. So we went from 0.43 to 0.56. So robust is making the standard error is just a little bit bigger. It's a more conservative approach. 7.56 and 0.914. So notice all the standard errors change a little bit, which is going to affect your t-values a little bit, and potentially affect your p-values. But that's what robust standard errors are. Just a slight adjustment in your standard errors, going to change your t's a little bit, therefore change your p-values, but your coefficients should largely stay the same. Okay. So if you do have that issue, you can move on and just do robust standard errors from that point on. Okay. So that's all the diagnostics, right? Kind of rehash, we got our data ready, we kind of explored it, we ran a full model, and then we went through we checked for multicollinearity, no issue in that case. We checked for outliers, doing Cook's D for standardized residuals, and then took those results, looked at how that compared to the lever 2 plot, generated a new variable called outliers. Everybody got a 0. We changed it to 1 if they fit the 3 that we identified. We compared those results and decided that ultimately it was better just to leave them in because they weren't changing things too much. And then we moved on to check if we had heteroskedasticity. And that's again if we're better at predicting one end of our higher levels of our outcome versus lower levels. And we do suffer from an issue here. So one of the options we have is to do nothing, and put that in here, is to just note that we have an issue with heteroskedasticity, but Allison argues that unless it's really severe, it's really not of concern. So that's one option. The other one would just be to use robust standard errors in doing a regression. and that just kind of inflates them a little bit to make it a little more conservative. So you could include the comma robust from here on out. Okay, so now you're ready to run your models. And at this point, we're going to use the SSTO and STAB. And here's where, don't just fall into the examples I give here. Think about how you want to model this. Okay, if you're going to have more than one model, what should be in model 1 and then what's in model 2? Okay, or model 3. There's a way to kind of think through. So think through some of the discussion on modeling. I'm going to go back to my results here. Notice in model 1, I just did mining status. And then in model 2, I kept mining status and added poverty rate. So that's what I'm going to do again. So we're going to go in here, pfair poor, and i.minestat. And then I'm going to do the if not missing and just everything. pfair poor, comma, minestat. Remember, you don't need to i.dot it in this part of the command, and ppov. And that way it'll make sure it excludes all cases that don't have values for all of those. And then I'm just going to erase that. Let me just copy that again. And this time I'm going to add ppov. Okay. So I'm going to run those two. And it's SSTO stands for store the estimates. Oops, if not missing. Okay. So I'm going to rerun those two. And it's going to store you can see it's storing the results in sort of a short-term memory. And then STAB will turn it into a table. I'm on my own computer, so I'm going to put in where I'm putting this stuff. So let me see here. I'm going to put it in this folder. I'm going to find the properties. I'm going to just copy that directory. And insert it. And I'll just call this, the folder was called OLS col. And I'll call this document example. Leave it as RTF. Now I had two models. So the title is whatever, fine. Model 1 and model 2. If I had more than that, I would have to add model 3 and so on. Now the SC stands for standard error. It depends on if you want the output to show the standard error or the confidence interval. I'm started to move toward confidence intervals just because it's more in line with the new statistics paradigm. B is your beta or your regression coefficients, and this is how many decimal places. So how many decimal places for your confidence interval, for your regression coefficients. If you were doing standard error, how many decimal places. And then R is your R squared. I usually do 4 for that. And everything else stays the same, so then I'll run that. And I get a link. So I click on that, and you get a relatively pre-formatted regression table. Now I mentioned that how I like to do my formatting on my categorical. I like to, I just have to play around here with trying to get this right. Borders and shading. I don't want that one. Okay. I'm trying to get rid of this line. So table properties. There. So I usually prefer to start with my categorical variable, in this case, mining status. And that's my variable. And then the categories, I'll just jump in a little and do this. And obviously, because it's a reference group, we don't need zeros for those. Well, that'll just be empty. And then for the other categories, I like to just indent those a little bit. Helps distinguish the overall categorical variable, which is mining status, from poverty rate, which is your other independent variable. Okay. And then everything else is pretty good. It uses two-tail by default, which is usually what I would recommend just sticking with, but you can put that in there. Confidence intervals and brackets. Yeah, and notice it's got the R squared. So that's where I got the table. Again, you don't have to do confidence intervals. You could do standard errors, but I'm increasingly moving in the direction of confidence intervals. So that's how you can get the table. Again, don't just follow along with these two examples of the model. Depends on how many models you have, depends on the how you construct those models. You got to tailor these. Okay. Now, if you were to ever go back and try to make some changes, make sure you, before you do that, do this ssto clear, and then make your changes and rerun ssto and stab. Otherwise, you're going to just get the same results over and over again. And you might want to change the RTF document. Okay. So I've got my regression results, my table, and then we go to the graphing options. Again, the coefplot is a post-estimation command, so it's going to use your last regression. If you just want to make sure, I'm going to grab my full model in this case, and get rid of the ssto, and we'll just rerun that model, and then I can get the coefplot. I don't have to change anything. And again, this is just a graphical representation of my estimates and their confidence intervals. And yes, it includes the reference group, which I can change the labels here and so on. But here's the effect of traditional. Here's the coefficient, basically 2.14, but then also its confidence interval. So basically, any value in this range is still compatible with our data. Just the most compatible is our estimate. Okay. And then you can see the effect of percent impoverished is lower. Now again, don't make the mistake of going, oh, well, the poverty rate effect is smaller than the mind stat effect. Remember, they're on very different scales. These are just, 0 ones going from 0 to 1, 0 to this status. They're just categorical comparisons of mean effects on the estimated value. This effect represents a 1 unit change in poverty rate. So yeah, it looks smaller, but if you just think that it's a 1 percentage point change, whereas these reflect going from no mining to removal, they're not in the same scale. So don't do kind of a head-to-head kind of comparison. Okay. So that's the coefplot. You can clean that up a little bit. The other option is to use these other commands. I don't particularly think you don't have to change anything. I don't particularly find them as attractive as the other ones, but you're willing to go with either. So that's just graphing the estimates and the confidence intervals. But what if we want to actually graph predicted values of percent fair poor at different levels of x? Okay, and we have two x's here, so we have to think about what we want. Let's just look at categorical first, which is what these commands show. So let me throw in, instead of cat var, mind stat. This command is just going to calculate, it's going to use the regression model, and it's going to calculate the margins or the predicted values of p fair poor at different levels of mind stat, holding the other variables, p-pob, at their means. Okay. So I just had to switch out cat var with mind stat. What do we got here? Oh, sorry, I need to rerun my regression. So let me rerun the regression, now rerun it. Okay. And then I can graph these things. I need to put in mind stat. And we'll just do the bar one. Okay, so what it does is it translates those margins into a bar graph of the margins. Again, the tops of the bars indicate the predicted value of p fair poor at different mining statuses, holding the poverty rate constant at its mean. Okay, so holding poverty rate at, I don't know, whatever it is, 20%. Holding poverty rate at 20%, what is our predicted rate of diminished health in non-mining counties? What is the predicted rate in traditional and removal? And you can actually get the numbers from the margins output, right? They're right here, 20, 22, and 26. Okay. That's what we would predict holding the poverty rate constant. Okay. And then, going back here, I'm not going to do the dot. If you wanted to look at poverty rate, one of the things we need to do is make sure we know what the range is on poverty. So I'm going to summarize p-pob if not missing all the ones, right? I could get this right earlier, but p fair poor MindStat, and pPOP. So I want to see what the range is. Okay, it ranges from roughly 4 to 38. So I'm going to use those to inform this margins command. So the int var is pPOP. The low value, I'm going to set it 5. It doesn't have to be perfectly at the minimum because sometimes there's very few cases at the ends. So I'm going to stick it to 5, and then the high value I'm going to put at 35. In the increment, I'm just going to, given that range, I'll probably just go with 5. Okay. What it's going to do is it's going to calculate a predicted value of p-fair poor when poverty is at 5%, 10%, 15%, and so on, up to 35. Right? And then it's going to hold mining status constant at the means. It doesn't really make sense, but that's what we're going to do. Okay, so that's the predicted values for poverty, and then we can plot them. So we can see that as we go across in poverty, holding mining status constant, here's what we would predict for the rate of diminished health as the poverty rate changes across counties. Okay, so low poverty, we're looking at about 12, 13%, and then high poverty, we're looking at about 32%. Again, you can see those numbers in the margins that we calculated. Okay. So that's how you can do an interval variable and show that, you know, here's the actual rate or the percentage of people reporting bad health at different levels of poverty, holding mining status constant. Now, given the situation, we can actually move on and do some interactions. Okay, so I'm going to skip some of these summary statistics, things like that, but let's go down to this predxcon. Okay, given that one of our variables, our independent variable is interval, and one is categorical, we can use predxcon, okay, because we have an interval independent variable. So I need to change dependent variable to p-fair poor. My x bar here is going to be the interval variable, and that's going to be pPOP. And we need to put in those values. I'm going to do 5 to 35 again. So F stands for from, T for 2, I for increment. I'm going to do 5. And then we're going to adjust for, but in this case we don't actually want to adjust for. Actually, I want to skip this one. I want to jump down to this command. I didn't realize I was. I'm going to grab this stuff and put it up. What I'm trying to do is interact mining status and elsewhere. Now, class means classification, or a class, sort of a categorical variable. It's unfortunate they use the word class, but that's part of the command, the generic command. So you leave that as. My categorical variable is MindStat. And then if we had other variables in our model, we would adjust for them here. So we would list, you know, whatever the other variables. We don't have any, so I'm going to get rid of that and then hit the graph. So if I click that, what it does is it calculates the regression behind the scenes, but then it looks to see if there's a significant interaction between the two. And if this p-value behind the scenes is less than 0.05, that indicates that there's a significant interaction. It's not. We don't see a significant interaction. Essentially, as you go up in poverty, there's always an independent effect of mining status. A little bit with traditional, there's a little bit of a departure from, you would expect this red line to be kind of right in the middle, evenly spaced. So there's a little bit in there, but not enough for this interaction term to be statistically significant. But basically, removal is bad for population health, no matter the poverty rate, and it's pretty consistent across the board. So low poverty to high poverty, the removal and even the traditional effect stay relatively the same. They're not contingent on one another. Okay? So that's one way in which we can do that kind of interaction. The only time we would do predxcat is if we're trying to interact two categorical variables. Okay, so that's when we would switch to predxcat. We don't have that here, but that's one other option. So that's categoricals. And in this case, I'd probably indicate that I ran the interaction, and I would clean up this graph, and I could include it in my write-up of, if that was part of my research question, I could include it in my write-up, saying, you know, beyond these analyses, an interaction was interaction effect between mining status and poverty rate was examined using, you know, predxcon command, and it found no significant interaction. But here's what, you know, those results look like. Okay. So that's how you do the OLS one. I know that's a lot. Hopefully you can just kind of review the parts that don't make sense, and we can certainly talk more about this in class.